Hello students, welcome back to our course Environmental Modeling and Simulation. By this time in our course, we have covered the basics of empirical modeling and we have developed an understanding of how to use ordinary differential equations to model systems that may be complicated and even complex, but are much easier when we use very simple basic graphical approach or say other mathematical principles. In this lecture and in the next lecture, I am going to discuss a model that was used few years ago to model the relationship between prosperity, growth in wealth, growth in global GDP and climate change. Now, typically climate change is modeled separately from economics, from GDP, and the climate change model may have anywhere from couple of variables to hundreds of variables. Climate change models can be extremely complex and typically require very high computational abilities. On the other hand, the economic models are also quite complex. Bringing the economic models and the climate change models together and trying to see how climate change and GDP are linked with each other is actually quite a challenging business. Now, the paper we are going to discuss is this particular paper, No Way Out: The Double Bind in Seeking Global Prosperity Alongside Mitigated Climate Change. This was published in 2012 by Dr. T.J. Garrett. Even though it's an old paper, it was quite a groundbreaking paper because it took what is extremely complicated system, climate crisis, climate change, and linked it with economics, which again typically tends to have extremely complicated models that are used. And the integrated models that people had used before this particular groundbreaking paper by T.J. Garrett typically involved hundreds of variables. So, some decent economic model with a medium complexity climate change model, together they have more than 100 variables, extremely high computational resources required and not feasible for day-to-day analyses or day-to-day understanding. But what T.J. Garrett did was the author highly simplified the system and reduced the resolution of both what is happening on the economic level and what's happening on the climate level to very simple terms, and used a thermodynamic based system which is frequently used in economics for modeling the flow of economical system to model both the climate change and the economics. So in this lecture, what we are going to do is we are going to see how T.J. Garrett built his model and what that model is about. So before we begin, let's look into how the climate change and economics modeling and also the policy has been in past few decades, including IPCC's SRES model, which is the most commonly used climate change and economics model. The assumption is that there is a way that we can mitigate climate change without affecting global prosperity, without affecting the economics. Now, T.J. Garrett's first premise in this model was that any kind of growth, whether it is economic growth, physical growth, material growth, any kind of growth, any kind of development requires energy, and human beings, human civilization are not an exception to it. So basically, the premise is that for a unit of growth, we require some amount of energy. And this is a particular factor, lambda, which we will discuss a lot as we build the model along with Professor T.J. Garrett. So the first premise, as I mentioned, is that any kind of economic growth requires energy input, requires consumption of fuel, which means there will be some combustion, some emission of greenhouse gases, and they will contribute to climate change. So basically, T.J. Garrett is questioning the IPCC SRES stand that there is a possibility to mitigate climate change and still maintain global prosperity, keep growing our GDPs. Explanation given for this assumption is that as we make our technology more energy efficient, as we make our technology more decarbonized, so that for a given amount of energy that is required for a particular work to be done, the carbon emissions are lower, it is quite possible to continue growing our economy like we have in past few decades and reduce or contain, at least contain, the amount of GHG gases, specifically carbon dioxide, in the atmosphere to a relatively safe level. Of course, we are way past the safe level now already. At the time of writing this paper, the idea was to maintain it below 450 parts per million. And now that doesn't seem very feasible to us. However, in economics, we have a different principle that we need to account for as we are looking into T.J. Garrett's model, and this is known as Jevons paradox. Jevons paradox is an economic observation that as our ability to use fuel becomes more efficient, it does not lead into overall reduction of the fuel usage. For example, during Industrial Revolution, there was a time when the availability of coal and the accessibility to coal mines became much more efficient. So instead of reducing the global coal usage, it actually boosted the global coal usage. And this is known as Jevons paradox, which is basically our ability to use fuels as it becomes more efficient. Instead of reducing our overall consumption, we increase the overall consumption. And there are typically two major reasons why Jevons paradox happens or why we observe it. The two common reasons are, first is a direct impact. Direct impact is that now it is more efficient to use the fuel, it's saving cost. So we can use the saved money that we have to invest in more endeavors so that we can use more of the fuel for more expansion of global wealth, for global prosperity, for increasing GDP. So this is a direct impact. Another example of direct impact is that, let's say, a house now spends less money on the diesel and the petrol that goes into their vehicles. So that household can now use that money to air condition their homes. And even though the efficiency of using fuel in the cars has improved, so less petrol and diesel are required, but that money, the saved money, was now used by the household to spend elsewhere, to use energy elsewhere, which is also going to contribute to GHG. The second kind of contributors that result in Jevons paradox are indirect. The indirect ones are basically when one particular industry in this whole economic system becomes more efficient, the advantages and the savings because of that particular industry becoming efficient are knocked down into other industries and other sectors, or knock-on effects. Now remember, the household that saved the fuel cost, additional fuel cost, because the energy efficiency of the vehicles improved, so they saved the fuel money on petrol and diesel, are now spending the same money on air conditioning or cooling their homes. Now, as a result of that, not only are they emitting the same amount or maybe even more amount of GHGs into the atmosphere as they were doing before, but they are getting better sleep, which means they are feeling healthier, they are happier, they are more productive as workers. So when they go back to work the next day, since they were well rested, they slept well, they are healthier, they are more productive in this capitalist economy, which means they are more capable of encouraging and assisting the economic system to expand, to use more energy, to increase the GDP, to increase the global prosperity and the global wealth. So these are indirect effects. Now, because of both direct and indirect effect, Jevons paradox says, as our ability to use energy becomes more efficient, we will not use less of it, we will not emit less carbon, we'll emit more carbon. This is the basic premise that the author of this paper has against the IPCC models. So let's build the model. Now, I mentioned that Garrett's model has very low resolution. And by that I mean, in economics, the economic part of the model, all the capital, whether it is labor, resources, they are all clubbed together. Human is not separated from the capital. Human is considered part of the capital. All the reservoirs, for example, all the natural materials that are used to fuel the capitalist economy that we have now, they are considered all at one level. There is no distinguishing done between them. The civilization as it exists, which includes our material properties, which includes our waste, which includes our energy like fuel that we use, for example, coal, LPG, petrol, diesel, gasoline, all of them are not distinguished from each other. They are all considered as one. The other thing is, since this is a thermodynamic based model, both first law of thermodynamics and second law of thermodynamics are used in this. So we have material reserves, which let's say maybe are fuel like iron, other metals, or trees, coal, oil, petrol, and they are at a higher energy, higher potential energy. So because of second law of thermodynamics, there is a tendency, or it is easy for that raw materials at higher energy state to move down to lower energy state where they're used by the system, where they're used by the civilization. So that once that happens, the material flows from the resources to the economic system, to the civilization. And then this economic civilization that is receiving the materials also dissipates, it loses some of the materials, and which we can call as waste materials, that are no longer useful for either the nature that is supplying the resources, nor for the humanity that's consuming the resources. So basically we have 3 steps in this energy system. The first step here is resources. The second step, so from resources things go to the second step. Second step is where the economic system is. And then from here things dissipate into the third step, which is the surroundings. And the surroundings are also dissipating some of the energy into the universe, which is an infinite sink, assumed to be infinite sink. So basically what is happening is that resources are at higher level, system is at second highest level, surroundings are at the lowest level. The system must continue consuming the resources if it is to remain at a higher level than the surroundings, because it is always continuously dissipating some energy to the surroundings. A simple example given in the paper is that the human body needs to continue consuming food on a regular basis in order to survive, otherwise it will keep losing its energy to the life processes and eventually the body will not be able to survive. This is a thermodynamic model that is frequently used for looking at economic flows. So here one possibility is for the economy to grow, for the system to grow, one possibility is that our ability to use the resources should grow. And the way to do that is to expand the available resources. So this is what's happening, and we'll see in the next picture, there's a very nice image from the paper. The resources, we may explore new energy resources, and that will increase the flow of energy from resource potential level to system potential level, then the system can grow. The other obviously is to reduce the dissipation, which since dissipation is quite natural, it will be very hard to do that. So the resources can expand when we explore previously unexplored resources. So this is one way. The other is that we can increase the rate. The other possibility is that we can increase the rate at which resources are consumed by the system by making this potential drop more efficient. And then obviously the next one, as I mentioned, is to reduce the dissipation, but that's not mostly in our control. Okay, let's look at the diagram from the paper. So this is the diagram from the paper. On left hand side is the thermodynamic model, on right hand side is its economic equivalent. So if you look at the thermodynamic model, the highest energy step is of accessible energy reservoirs, right? They are at the higher potential, and then from higher potential they'll go to the lower potential, which is the system. And then the third potential is the surroundings, where the dissipation happens. Now, the use of accessible energy resources can increase, so we can get newly accessible energy reservoirs, so that's where the expansion that can happen there. The interface between the highest potential level of resources and the system, which is at the second potential, that is where the actual transaction use of energy or transfer of energy from reserves to system is happening, and that interface is very important. So let's say the potential drop per unit here at the interface is del U, and the number of units material units available in the interface is given by this particular sign, this sign. So if I multiply del U and this sign, this is giving me an idea of the size of the interface. Again, thinking from thermodynamics perspective, this is telling me about delta G, which is the energy difference between the reservoir potential level and the system potential level. Alpha here is your efficiency. It's a constant, maybe not constant, but it is an efficiency that tells me how the reserves are being used or how the energy is being transferred from high potential to lower potential, and that is A. A is the rate at which the system is being heated up. A is the rate at which the reservoirs, the energy reservoirs are being used. Remember, the energy reservoirs here can be fuel, they can be other natural raw materials that are used. Let's just remove natural, let's just say raw materials that are used. So A is equal to alpha delta G, which we have established is alpha this. So this is, remember, number of material units, and this is the potential per material unit. Now, the other thing is the interface itself can expand. Our ability to use the resources itself can become more useful for us. So, let us say the interface is expanding at W rate. So, W here is delta U, which if you remember is the potential difference between the reservoir and system per material unit multiplied by the rate at which the material units are changing. The faster the material units that are being transferred from reservoirs to the system change, the faster the interface expands. And then obviously there is dissipation happening. The first law of thermodynamics stands true because the system is continuously being heated up, but it's also losing heat in a dissipative way to the surrounding. The second law works because the movement, the energy flow is happening from higher potential to lower potential. Okay, very important thing to understand here is that the wealth generation is not decoupled from energy combustion, energy use. Energy use is required for generation of wealth. The rate at which the system grows is basically the production. It tells me about the rate at which the wealth grows in this model. Now, another thing that we need to understand is that the potential energy difference between the reservoirs and the system, which is guiding the movement of materials from reservoirs to systems to surroundings, is also making sure that the system does not decay. If this fall stops, if the uptake of reserves stops, the system diminishes, it starts decaying because it's always losing dissipatively to the surrounding. Another thing we need to understand is that energy consumption here is intrinsically linked with the wealth generation. So, energy consumption So, C here is global wealth, and basically what we are saying, energy consumption A is linked with global wealth. Now, lambda here may or may not be constant. The premise of this model is that lambda is constant, and very soon we will see that the author actually took up the data for many decades and saw that lambda here has been quite constant over many decades. And if this hypothesis is not true, then we can reject the whole model. But so far, this hypothesis is true, which is that certain amount of energy consumption is required for certain amount of increase in global prosperity when we have accounted for inflation. Okay. Now, the other thing we need to understand is a gross world product, how we are defining gross world product. So, let us say the productivity in this particular model, productivity is P, right. In this model, P is defined as dC by dt, the rate at which wealth changes. See, basically if productivity in one particular year is P and we multiplied it with the time duration del t, which typically economic model is 1 year because the economic indices are often updated year wise. So, this basically is the GWP. GWP is gross world product, the amount of product that was produced basically by energy consumption, energy transfer in the given year. And the more production we do, higher the P is, more the wealth increases. So, this is another very important part of the model, which is that we can define C, which is the wealth here, as an integration of productivity over time, economic productivity. Or a summation of gross world product over time. So, if we add the gross world product of all the time since humanity has existed, we will find out the net wealth of the human civilization. Okay. Now, if we look at the equations that I have written on this page, we can very quickly get more information. First is that, as I mentioned here, it is clear dC by dt is equal to P. So, the rate at which the wealth, global wealth changes is equal to the productivity. And the other thing is, since productivity is dC by dt, if we look at the equations here and we put them in this system, what we get is P is also equal to 1 by lambda dA by dt. Remember, lambda gives me the ratio. So, if you go back here, lambda gives me the ratio between A and C, amount of energy required for given amount of global wealth. Now, since I am talking about global wealth, global productivity, please note here, This system is true when we take the human civilization as whole. That is the resolution of this system. If we look at it country-wise, this system may not work. And I'll talk more about it later. Okay, so this is, if we combine those two systems, this is what we get. So again, we can write down the A, what we have defined A as, and then this becomes let's spend a few minutes looking at this particular model that we have arrived at. The rate at which the wealth is changing is equal to productivity is proportional to the rate at which the energy consumption is accelerating. So, if we want to be productive as economy, if we want global wealth to continue increasing, then the rate at which we are using our reserves, our reservoirs, our energy reservoirs, that also has to be positive, which means the number of material units that we are using per given time has also to be positive. So, this is a very important point. Now, on the other hand, we can integrate this and talk about global wealth. So, if you want to maintain the global wealth, or if you are okay with collapsing the economy and letting the global wealth decay, we just have to integrate this system. So, C, which is integral of P, will become, let's say if we integrate these, so this is coming directly from what I wrote here. Yeah, instead of keeping P, I have just substituted this. Yeah. Now, as I mentioned, the author has noted that lambda it seems to be constant. So, we took the constant out. Okay. Then this can also be written as this. So, there is a direct proportionality between global wealth, the rate at which we are consuming the energy, we are basically emitting GHGs, and the rate at which the material units which we are using are increasing. So, these three are directly linked with each other. This is the basic model. Now, the author also introduces a different term, which is this. This is information on return. The author introduces a new variable which represents return, and the return is basically the rate at which the energy difference between the two potential is changing with time. It is also proportional to the rate at which the material units are changing with time, the rate at which energy consumption is changing with time. They are all linked with each other, and the rate at which global wealth is changing with time. So, this should give you an idea. If the GDP has to grow, our energy use has to grow, our material units that are consumed has to grow, the potential difference between the first two layers has to grow. Only then the global prosperity will grow. That is the basic premise of this model. Now, let us look at a very important part of designing this model, which is model validation. So, what the author did was, after writing these mathematical equations, now students, if we look at what we have studied in this course, basically here the genius is in using the thermodynamic model to model the economy of our earth. The genius of the author is actually in reducing the resolution of the model. One of the things that I have talked about over and over again during the course is that when you design models, the more we simplify it, the easier it is to understand, to interpret, but not necessarily more representative of what is happening in reality. However, there are advantages of both: increasing the resolution, adding more variables that are having significant impact on your output, and also reducing your resolution, minimizing the amount of variables you are using. For example, here for economics, all we are looking at is the number of resources, the rate at which resources are being consumed, the energy difference, the material units, the rate at which wealth is being generated, and the return rate. That is it. That is all we are looking at. And we have already linked the global prosperity with the energy consumption, material consumption. Now, for material consumption to carbon emission is a very simple answer. If we assume that average our fuel has this much amount of carbon, so for generating these many kilojoules of energy and using this many kilojoules of energy, this much carbon would be released. If we have that very simple linear equation, we have linked climate and economy. So, you see, this is a very simple model. It works when we look at the whole human civilization as one, not on country level. So, the resolution is extremely low. But during model validation, the author noticed that when we take the wealth accumulated for last 2000 years of humanity, and when we look at the energy consumption, the rate of heating, the wealth generation, the productivity over last many decades during industrial revolution, we notice that the basic premise of the model stands true, and the basic premise is lambda is constant. So if we go back to what lambda is the ratio between A and C, the energy consumption and wealth generation. And actually over past 40 years. And actually since 1970, the value of lambda has been constant at lambda is equal to 9.7 plus minus 0.3 milliwatt per 1990 US dollar. Now US dollar 1990 is important because this value accounts for inflation. Here is an example of a very simple model that holds true for Earth as whole, not for more resolution, but it works really well. And it also questions many other models, more complicated models that we have been using. Okay, another thing in this model is looking at the rate at which the interface is increasing, the rate at which the work which is done by the system to consume their energy reservoirs and convert it into material gains of the civilization, the wealth of civilization, W, changes over time. If the interface increases, then more work would be done. So this is W here. So another thing that the author adds in this model is that the work is done proportional to the energy that is consumed, and the constant here is efficiency constant. Now we can change the efficiency at which the fuel works. We can make our systems more efficient. So if we change the efficiency, then we need to consume less. We need to consume less heat. We need to release more heat from reservoir level to the civilization level to get the same amount of work done, right? Now, this is where the Jevons paradox, which I introduced you to earlier, comes into picture and says, this is going to backfire. If we reduce the efficiency, it will require less energy to get the same amount of work done, but then the remaining energy will still be spent by the civilization to get additional work done, to continue growing the global wealth. Okay, now here is one major problem. The problem is that if we continue, despite getting more energy efficient in our ways our industries and our technologies work, if we are going to continue emitting the same amount of carbon dioxide, we are going to continue using same amount of energy, because the net A is not going to go down. If it goes down, as we saw here, if dA by dt becomes negative, then the wealth will go down, material use will go down, productivity will be negative. Basically, we are talking about economic collapse. So Jevons paradox is actually saving us from economic collapse. But if that happens, then worst case scenario, climate crisis will become more and more intense, more and more severe. As a result, the climate induced extreme events will destroy the global wealth. So if you look at C is directly proportional to the rate at which we are consuming energy. The global wealth is directly proportional to that in this model. But it is also affected by the natural decay. It's also affected by natural decay and climate induced damages, extreme climate induced. What this model is very successfully able to show is that if we make our system more energy efficient, the A will continue increasing, the wealth will continue increasing, but because of the climate, because of the emissions, the extreme events will increase and the extreme event induced damages will increase. So here we introduce another term, which is the carbonization of the fuel term. C, small c, not the capital C. Capital C is wealth, remember, and small c is the carbonization factor. Carbonization factor, as I mentioned briefly earlier, tells me about how much carbon is there in the fuel. So carbonization is basically emissions by use of resources. So E and A can be measured, and C obviously by the ratio we will get it. Now C is not necessarily constant, we can decarbonize our fuel. So instead of using coal, high carbon fuel like coal, petroleum products, we can go for less carbon rich fuel or no carbon fuel, for example solar energy, hydro energy, wind energy. So when we decarbonize our fuel, we are reducing the emissions amount of heat transfer per amount of resource consumption. And now the question is it going to impact our global wealth production? So for that, what we found out was the rate at which emission in this model is that the rate at which the logarithmic natural log of emissions, E capital E is emission by the way, the rate at which emissions will change over time is equal to the return factor and the rate at which the carbonization changes over time. So if we want to reduce emission, we need to do two things. We need to reduce the rate of return. Now, rate of return is on what our global prosperity depends, if you remember. Rate of return goes down, the economy is collapsing. So we can't let this be negative, we can't let this go down. What we need to do is we need to rapidly decarbonize our economy. So even before modeling this, just writing the equations down, TJ Garrett is already giving us a very good glimpse into, according to his model, how the system works, how the economy, how the emissions are linked with each other. Now, for overall emissions to go down, for this to be negative, the decarbonization has to be faster, more in magnitude than the rate of return. So, we have to rapidly decarbonize our economy. Now, in this model, TJ Garrett made sure that they accounted for inflation. So, if you read the paper, I am not going to go into the details of the economics part, but if you read the paper, they have accounted for inflation in both the productivity, global wealth. So, using this basis that we have discussed so far, the author presented or put this together to make the model, which is the groundbreaking model as I mentioned. It is known as C-Therm model. And we are going to discuss C-Therm model in the next lecture. So, stick around. This is a very important model and also the conclusion of our course. Thank you.